So now we're going to start taking a look at some examples of how to figure out where a function is increasing, where it's decreasing, and the coordinates of the relative extrema. For our first example, I want to look at the function f of x equals x cubed minus 3/2 x squared. Take a moment and copy that down, and then we'll talk about how we'll do this together. The first thing that I need to do is I need to find my critical values, and I'm going to plot them on a number line that I'm going to label f prime. Step number 1, I need to find the critical values and I need to plot them on a number line labeled f prime. First thing I'm going to do is I'm going to find my critical values and plot them on a number line that I'm going to label f prime. Well, how about you take a moment, go find your derivative, go find your critical values and send those into Edpuzzle. F prime of x is going to equal 3x squared minus 3x, 3/2 times 2 gives you minus 3x. I'm going to do some factoring. Let's see, 3x times x minus 1, and it looks to me like I have critical values at x equals 0 and at x equals 1. I'm going to make a number line. I'm going to label this as f prime. I'm going to plot my critical values at 0 and 1. The logic here is the only places where my function can change from increasing to decreasing or decreasing to increasing is at a critical value. So 0 and 1 are the only places where things could change. So I need to do some analysis here and see, is the derivative actually changing at 0? Is the derivative actually changing at 1? This is now going to go back to something similar to something from the summer work. I'm going to test each region to determine the sign of f prime. I want to see if any x value that I plug in before 0 would give me a derivative that is positive or negative. And then same with between 0 and 1, and then same with between 1 and 2. Step number 2, I'm going to test each region to determine the sign of f prime. I'm going to test each region to determine the sign of f prime. So I'm just going to recopy that number line so it's following example number 2. Maybe I should make the video pause for a moment so you can finish getting caught up with copying. I'm going to take a number over here and I'm going to plug it into my f prime. Maybe x equals 2. F prime is going to give me 3 times 2 times 2 minus 1. 3 times 2 is 6 times 1 is 6. All I really care about, though, is that 2 gave me a positive answer. And in fact, any number that you plug in that is greater than 1 to the derivative, by the way, I'd plug into the factored version of the derivative, will give me a positive answer. Let me go and plug in something between 0 and 1, like x equals 1/2. F prime then is going to be 3 times 1/2 times 1/2 minus 1. Well, positive, positive. 1/2 minus 1 is some sort of negative number, so a positive times a negative will give me a negative number there. And I know that the second region is negative. I'm going to plug in something like x equals negative 1. And I'm going to get a derivative that looks like 3 times negative 1 times negative 1 minus 1. Negative times a negative gives me a positive, times a positive gives me a positive. Your signs are positive, negative, positive. No, I'm not actually going to need to see this plugging in work. You can just sort of do the plugging in your head. And again, I would focus on the factored version. I'm also going to put some little symbols over here. Where the first derivative is positive, I know my function's increasing. Where it's negative, I'm decreasing. Where it's positive, it's increasing. I now have all the information I need to be able to reach some conclusions. Step number 3. I'm going to analyze the number line and this is a really big deal for the AP exam, justify your answers. Which just means explain how you know we're increasing or decreasing or have a relative max or a relative min or whatever. I know that I'm increasing where f prime is positive. That's also why I do those little symbols there. I'm increasing over here, and I'm increasing over there. I'm going to say increasing from negative infinity to 0, and then again from 1 to infinity. Why? Well, because f prime is positive there. And that's how I'll write out my justification. You go write out where we're decreasing with a justification. Decreasing where f prime is negative, so between 0 and 1. Why? Because f prime is negative there. As for my relative extrema, I have a relative max at the point. Well, let's see. A max occurs where f prime changes from positive to negative. And I kind of see over here, looking at my little increasing, decreasing things, looks like the max is going to happen right over here at x equals 0, because f prime is changing from positive, going up, to negative, going down. There's a relative max at the point 0, comma, something that I'll figure out in a moment. Why? Because f prime changes from positive to negative there. But I now need to get a y-coordinate. If I have my x-coordinate of 0, where am I going to find my y-coordinate from? What am I going to have to do? We've got to go back to the original. The original function always tells us y-coordinates. We're going to get 0 cubed minus 3 halves times 0 squared. That's just 0. There's a relative minimum at, well, I need my f prime to change from negative to positive, f to be changing from decreasing to increasing. That's happening at x equals 1, comma something. Why? Because f prime changes from negative to positive there. And these are the justifications you will always need to use for increasing, decreasing, relative max, relative min. Do not say it is changing from negative to positive. Well, what is? F prime, in a moment we'll deal with f double prime. I need to know specifically what function is changing, so in this case, f prime. Take a moment, go find your y-coordinate. 1 comma, what? I'm going to go back and plug into the original. F of 1 is 1 cubed minus 3 halves times 1 squared. That is 1 minus 3 halves, negative 1 half. 1 comma negative 1 half. That's a negative in case you couldn't tell. Negative 1 half is where we have our relative minimum. Take a moment, go graph this, either on your calculator or on Desmos, and see if the graph actually agrees with what we're saying there. Hopefully when you looked at this, you saw that, yep, it was doing exactly what our analysis said. I want to show you 2 more examples. Not going to write the directions, but it's going to be the same as last time. We're going to figure out where this function is increasing and decreasing. So relative max, relative min. Let's look at f of x equals x squared minus 4 to the 2/3. Take a moment and go find your derivative. I'm going to get f prime of x equals 2/3 times x squared minus 4 to the negative 1/3. And by chain rule, I'm going to multiply it by 2x. And I might as well clean this up into f prime of x equals 4x over 3 times the cube root of x squared minus 4. Take a moment and go find your critical values. From the numerator, I'm going to get x equals 0. From the denominator, x squared equals 4, so x equals plus or minus square root of 4 plus or minus 2. I have critical values of negative 2, 0, and 2. I'm going to go deal with my number line. And maybe I can do this by just sort of thinking about things. If you plug in a number greater than 2, like 3, the top is positive. 3 squared minus 4, that's a positive. Cube root of that's a positive times 3 is a positive. A positive divided by a positive will give me a positive. See if you can go through some similar logic to fill in the other parts. And if you're not liking this, totally fine. Just plug in our number in those regions, and that will work as well. See if you can fill in the rest of your number lines. Between 0 and 2, if I plug in 1, 4 times 1, that's positive. 1 squared minus 4, that's a negative. Cube root of that, you can do the cube root of a negative number. You get a negative number. Negative times a positive is a negative in the bottom. Positive over a negative, we'll make that region negative. Plug in negative 1. Negative 1 squared is 1 minus 4 is a negative. Cube root of a negative is a negative. Bottom is negative. 4 times negative 1, top is also negative. Negative over negative will make this positive. Plug in negative 3. Negative 3 squared is 9 minus 4 is a positive. Cube root of a positive is a positive. Bottom's positive. 4 times negative 3 is a negative. Negative over a positive is a negative. Write out the increasing and decreasing stuff. We should be increasing from negative 2 to 0 and then 2 to infinity because f prime is positive. Decreasing from negative infinity to negative 2 and then 0 to 2 because f prime is negative. Continuing, see if you can figure out where we have a relative max, the coordinates, and same with the relative min. Let's see, it looks like I have a relative max at, relative max at x equals 0, comma, I'll find my y coordinate in a moment, because f prime changes from positive to negative. Looks like a relative max over there. As for the y coordinate, I'm going to go back to the original, 0 squared minus 4 to the 2/3, negative 4 to the 2/3. Oh, this isn't going to be great. I might as well square that negative 4 and get 16, cube root of 16, which would be fine. If you feel like simplifying it, you could do that. You could say cube root of 8 times 2, 2 times the cube root of 2. That would also work, but I'm fine with cube root of 16. Relative min. Actually, there are two relative mins. One over here, one over there. Negative 2 comma something, and positive 2 comma something. Why? Because at those places f prime changes from negative to positive. And I need to go plug those into the original. So f of negative 2 equals negative 2 squared. That's 4 minus 4 to the 2/3. That's 0. Going to get something similar over here. F of 2 is 2 squared minus 4 to the 2/3. 4 minus 4, 0 to the 2/3, 0. And I've got that one. Go graph and see if what your graph looks like agrees with what we just calculated. One final one. F of x equals x squared minus 3x minus 4 over x minus 2. I'd like you to take a moment, use your quotient rule, and see if you can find the derivative, and then stop. Low, d high, minus high, d low, draw a line, and square below. We're getting that. I do have to clean this up quite a bit. 2x squared minus 4x minus 3x plus 6 minus x squared plus 3x plus 4 over x minus 2 squared. And that becomes x squared minus x squared, that's x squared, minus 4x plus 10 over x minus 2 squared. I now need to find the critical values. Denominator is going to give me a critical value at x equals 2. The numerator, I can't factor that. And we're not allowed to use a calculator for this, so solving by graphing is out. How else can you set the numerator equal to 0 if you don't have a calculator? Hopefully you said quadratic formula. Let's go for it. X equals negative b, 4, plus or minus square root of b squared, 16, minus 4 times 1 times 10, all over 2 times 1. X equals 4 plus or minus square root of 16 minus 40. That's negative 24. Which means I'm not getting any real values from the numerator. There are no critical values coming from the numerator. I only have x equals 2. So, how about you take a moment and see if you can finish off the analysis with your number line. By the way, make sure you are labeling your number lines. We'll see later on in the unit, we're going to be dealing with like 3 number lines at a time, and we've got to know what's what. Label that number line f prime. Go do your analysis. Plug in 3. 9 minus 12 is negative 3 plus 10 is a positive. Bottom is always positive because of that square. So positive there. Plug in 1. 1 minus 4 is negative 3 plus 10 is positive. Bottom again is always positive, so positive there. I think I'm increasing basically everywhere. But you know what? I shouldn't include x equals 2 because at x equals 2, f prime is not positive. So I'm going to say I'm increasing from negative infinity to 2, and then again between 2 and infinity, because f prime is positive there. Take a moment and go graph that. Hopefully your graph, was positive everywhere, increasing everywhere, except at x equals 2 where we had that vertical asymptote. In the next video, so right now we know about when our graph's going up and when it's going down, but there's a little bit more to the shape of our graph. Going up like this is different than going up like this. And in our next video, we're going to talk about what we call concavity that will help us refine the shape of our graph a little bit beyond just going up and going down.